Did you hear the one about the tortoise beating the hare? Now imagine the tortoise is sound, and the hare is a beam of pure light. From a small lab at the fictional Middle State University in Tennessee, a truly wild claim has emerged. A team, a mix of bright graduate students and even some ambitious high schoolers, announced that they had clocked sound moving faster than light. This isn't just a bold statement, it's a direct challenge to the foundations of modern physics. A claim so profound that if it were true, textbooks would need to be rewritten from the ground up, and Albert Einstein himself might have to posthumously reconsider his life's work. The news spread like wildfire across the internet, sparking a mixture of awe, disbelief, and intense curiosity. To understand the claim, we must first understand the experiment. At its core, the setup at Middle State University was straightforward, designed to stage a direct race between sound and light. A student-led team placed their devices at one end of the lab, a sound source, likely a speaker producing a sharp, distinct pop, and a light source, such as a fast-flashing LED. At the other end, a carefully measured distance away, they positioned their detectors, a high-sensitivity microphone to catch the sound, and a photodiode sensor to register the arrival of the light. The idea was simple: trigger both the sound and the light at the exact same instant, then use a high-precision timer to see which signal reached the finish line first. According to their published data and accompanying video logs, the results were consistent and startling. In trial after trial, the electronic signal from the microphone was registered by their timing device, fractions of a second before the signal from the light sensor. The time difference was minuscule, perhaps just a few nanoseconds or microseconds, but it was undeniably there in their logs. The students meticulously documented their process, showing their equipment, their raw data tables, and their calculations. It's this apparent thoroughness that made the claim so intriguing. This wasn't just a wild guess, it was a conclusion based on what appeared to be empirical, repeatable measurements from a controlled laboratory environment. They had the numbers to back up their extraordinary headline. To fully grasp the magnitude of the MSU claim, we need to step back and appreciate the rule they say they broke. For over a century, the speed of light has been the undisputed cosmic speed limit. It's not just a fast number, it's a fundamental constant woven into the very fabric of space-time. The great Albert Einstein, in his theory of special relativity published in 1905, established this principle. The speed of light in a vacuum, denoted by the letter c, is approximately 299,792 kilometers per second, or about 186,282 miles per second. It's so fast that a beam of light could circle the Earth more than 7 times in a single second. It is, as far as we know, the universe's ultimate speed. In stark contrast, the speed of sound is far more modest and variable. Sound is not a fundamental thing like light. It's a mechanical wave, a vibration that needs a medium to travel through: air, water, solid objects. In the air at room temperature, around 20 degrees Celsius or 68 degrees Fahrenheit, sound ambles along at about 343 meters per second, or roughly 767 miles per hour. That's incredibly slow compared to light. It's why you see the flash of lightning seconds before you hear the clap of thunder. The light reaches your eyes almost instantly, while the sound wave takes its time traveling through the air to reach your ears. The difference isn't small. Light is nearly 1,000,000 times faster than sound in air. It states that nothing that carries information or energy can travel faster than the speed of light in a vacuum. This isn't just a suggestion, it is a cornerstone of physics upon which countless other theories and technologies are built. Everything from our GPS satellites, which must account for relativistic effects to remain accurate, to our understanding of nuclear energy, E equals mc squared, relies on this principle being true. The phrase faster than light is electrifying, but in physics it can also be misleading because there are weird, counterintuitive situations where parts of a wave can appear to exceed light speed. However, these scenarios come with a huge asterisk. They don't actually violate Einstein's cosmic speed limit, because they don't transmit any information faster than light. One such phenomenon is phase velocity. Imagine a long ocean wave approaching the shore at an angle. The crest can seem to race along the shoreline faster than the wave moves forward. That moving point of phase can appear superluminal, but it's just a geometric illusion. It carries no energy or signal. Another example is group velocity in special materials. A light pulse made of many frequencies enters an engineered medium, and the peak can be reshaped so it seems to exit before fully entering. That makes the peak look superluminal, but the front edge, the bit that carries new information, never exceeds c. These effects are fascinating but are mathematical artifacts, not violations of causality. They don't let you send messages back in time or instantly chat with someone on Mars. Could MSU have seen one of these effects? Very unlikely for a sound wave in air. Sound in air is extremely well understood. When an experiment yields a result that defies a century of established science, the first place to look for an explanation is not in rewriting the laws of physics, but in a far more common culprit: systematic error. In any measurement, there are tiny hidden flaws that can conspire to create a misleading result. Think of it as a detective's checklist of usual suspects. The most likely suspect in a race between sound and light is sensor delay, also known as latency. The microphone and the light sensor are not magical devices. They take a small but finite amount of time to react and convert stimuli into electrical signals. If the microphone's internal electronics are even slightly faster than the light sensors, it will create the illusion that sound arrived first. Another prime suspect is the trigger mechanism. The experiment depends on the sound and light being generated at the exact same instant. But how can we be sure they were? If the electronic command to fire the speaker was processed a few microseconds faster than the command to fire the LED, the sound would get a head start. This trigger offset is a classic source of error in timing experiments. Even the cables connecting the devices to the timer can play a role. A longer cable on the light sensor's side would introduce a tiny delay in the signal reaching the timer, making the light appear slower than it actually was. Every single component in the chain must be perfectly synchronized. The physical environment itself presents more suspects. The path length for both signals must be measured with extreme precision. If the sound wave had a slightly shorter or more direct path to its sensor than the light beam did, it would have an unfair advantage. Furthermore, the speed of sound is notoriously sensitive to environmental conditions. A draft of hot air, a change in humidity, the presence of other gases could slightly alter the sound's travel time in unpredictable ways. Finally, we must consider the possibility of errors in data handling and interpretation, software bugs, incorrect formulas, or miscalibration, manufacturing a false result. The story of the MSU experiment highlights one of the most important, yet often overlooked aspects of the scientific process: peer review, independent replication. A single result from a single lab, no matter how exciting or well documented, is never the final word. It is merely the beginning of a conversation. The real test of any scientific claim is whether other scientists in other labs using their own equipment and their own methods can achieve the same result. This principle of reproducibility is the ultimate quality control mechanism in science. It is what separates a one-time fluke or a local error from a genuine universal discovery about the nature of reality. The role of the students in this experiment is something to be celebrated. Involving young minds in hands-on research is crucial for fostering the next generation of scientists, engineers, critical thinkers. It teaches them valuable skills in experimental design, data collection and analysis. That's why the scientific community functions as a global, collaborative, and skeptical team. When one group makes a claim, other groups step up to test it, challenge it, and try to poke holes in it. This isn't an attack, it's how science gets stronger. Imagine if the MSU team's results were published in a peer-reviewed journal. Other physicists and engineers around the world would read their paper, scrutinize their methods, and analyze their data. So, where do we stand on the extraordinary claim from Middle State University? At this moment, on June 4, 2026, the claim that sound moves faster than light remains an unproven and highly suspect assertion. While the story is exciting, the student-led effort is commendable. The finding flies in the face of a mountain of well-established physical laws and a century of experimental confirmation. The history of science suggests that when results violate fundamental principles, the cause is usually a subtle, experimental error. The most probable culprits are timing delays in the sensors, the trigger electronics, creating an illusion of superluminal speed. The scientific method has a built-in, self-correcting mechanism for occasions like this. The claim has been made, and now the process of verification must begin. If they consistently reproduce the result and can definitively rule out every possible source of error, then we will be on the cusp of a true scientific revolution. But until that day comes, and it is a very big if, treat the claim as a fascinating question, not a proven fact. For now, the cosmic speed limit remains in the hands of light. Established physics is safe. Thank the students at Middle State University for sparking this conversation. By making a bold claim, they gave us a chance to revisit the foundations of physics and to appreciate the rigorous, self-correcting nature of the scientific process. Thank you for joining me on this deep dive into a mind-bending claim. If you enjoyed this exploration and want more stories breaking down the science behind the headlines, please consider liking this post and subscribing for more content. Your support helps us continue to explore this amazing universe together. Thank you again.